When we talk about concentration, we're talking about how much solute is dissolved in a solvent of a solution. If we're talking about aqueous solutions, then we know that the solvent is water. There are different types of solutions. You can have a solid-solid solution, which is called an alloy. It's typically made up of different metals that are mixed together. They're not bonded, they're just mixed together. So brass, steel are examples. Solid liquid solutions, that's like your salt water, any of your ionic compounds in water. Liquid, that's like wine. Wine is ethanol and water. You could have gas and liquid, which is like your fizzy drinks, so carbon dioxide and water. You could have a gas-gas solution, like air. So all sorts of different combinations of our phases can be put together to make solutions. Concentration, the symbol for concentration is a lowercase c, and it's equal to the amount of solute measured in moles divided by the volume of solution measured in decimeters cubed. Notice that the volume here is in decimeters cubed. We typically use square brackets to show concentration. So we have H2, and those square brackets show that this value of 1 is moles per decimeters cubed. The formula for concentration, C equals N over V, N is for moles, is given to you in your data booklet. We can rearrange that so that moles is equal to C times V, or concentration times volume. That one's not given to you in your data booklet, so you need to be able to solve for concentration or moles or volume using this ratio. So known concentrations are prepared in a very careful way. You usually mass the solute using an analytical balance. This is a picture of an analytical balance, and the one that was in my classroom was on the back counter next to the column, and only the DP students will use this analytical balance. So you never used it in MYP because this balance can cost $1,000 or more. It does go out to more decimal places. Analytical just means it's more precise or goes to more decimal places. So you measure out the solute, and then you carefully put it in a volumetric flask. A volumetric flask looks like this. It has a line that is for a specific volume. This picture is showing us 100 milliliters. So you would put some water in there, you would put your solid in there, and then you would slowly add some water, mixing it constantly. Once it's all dissolved, then you would add enough water to reach that exact line, and then you would have that precise volume and that mass, which you can convert to moles, and then you can find your concentration. If it is a liquid, like an acid, and you're diluting the acid, you would always want to make sure that there's some water in the volumetric flask before you add your specific volume of acid and then dilute it to that level. So some problems, well, let's go over a couple of them. We have a mass of sodium chloride. We're dissolving it in a given volume, and it wants us to calculate concentration. So we know concentration is equal to moles divided by decimeters cubed. So we're going to have to convert grams to moles and centimeters to decimeters cubed. So let's deal with the moles first. So we just set up a little table, bring our unit and substance to the bottom, and we're converting it to moles on the top. And we know 1 mole is equal to the molar mass. So on the periodic table, sodium plus chlorine, and we get a molar mass of 58.44 grams per 1 mole. So when we multiply and divide, the grams would cancel. And we would have 3.657 moles if we keep our significant figures. Then we need to convert centimeters cubed to decimeters cubed. So remember, King Henry died unusually drinking chocolate milk. You're going from centimeters to decimeters, so that's one place to the left. However, it's cubed, so you're going to want to move that 3 times. So 500 centimeters is 0.500 decimeters cubed. So to find our concentration, we're going to take our moles and we're going to divide it by decimeters cubed. And we have a concentration of 7.31 moles per decimeters cubed. Notice we're using that negative sign to show that the volume is in the denominator. So looking at another example, this time we're looking for grams of the potassium hydroxide, and we have our volume and we have our concentration. So remember, concentration is equal to N over V, so we can solve for moles and then convert it to grams. To do that, we would need to multiply by volume on both sides. So our volume times our concentration, the decimeters cubed would cancel, and we would have 2 moles, and then it's potassium hydroxide. Remember, potassium is in group 1, so it's +1. Hydroxide's a polyatomic with a -1 charge, so it's KOH. And then we can convert that to grams, bring our unit and substance to the bottom. And we know 1 mole, and then we go to the periodic table to find the molar mass. And we have 56.11 grams. So when we multiply and divide, the moles cancel. And we have 2 significant figures, so we would say 110 grams of KOH. Sometimes you might see concentration done in parts per million. So this is useful when we describe very low concentrations found in air or water pollution. So typically you only see this in environmental chemistry, but it's the mass of the component divided by the total mass of the solution times 100, so it's kind of like a mass ratio. And since it's done by mass, then temperature, it doesn't matter what the temperature is because it's not dependent on it. Dilution is another useful thing we use in chemistry, so that's when you have a solution and you need to change the concentration, and you do that by just adding water. So you have C1 times V1 equals C2 times V2. Because you have 2 different volumes, the unit of volume wouldn't matter because the units would cancel out. So you could do this in centimeters cubed, you don't have to do it in decimeters cubed. The concentration, though, has to be done in decimeters cubed. So in our example here, determine the final concentration of 75 centimeters cubed solution of HCl. And then it gives us the concentration, and it says it's diluted to a volume of 300 centimeters cubed. So this is our C1 and our V1, and then we're diluting it to 300. So what is the final concentration? And since we're solving for C2, we know we would have to divide both sides by V2. So we would have 0.40 moles per decimeter cubed times 75 centimeters cubed divided by 300 centimeters cubed. So see, the centimeters cubed would cancel out, so it doesn't matter if it's in centimeters or decimeters. Multiply and divide. We would want 1 significant figure because our 300 centimeters cubed is 1 significant figure. So the answer would be 0.1 moles per decimeter cubed as our new concentration. Notice that as volume increases, the concentration should decrease. So that is something that you can watch out for. Looking at another problem. So here we have a volume and concentration. So this would be C1 and V1. And we're changing the volume to 750. So we want to know what the concentration would be. So we would take our formula and we would divide by V2 to get C2. So we're going to take our 0.1 moles per decimeters cubed, multiply it by the 250 centimeters cubed, and then divide it by 750. Again, the volume unit didn't matter because we're simply canceling those out. We would want two significant figures because all of those numbers have two significant figures. Remember 0.0, that 0 is not significant, so you still have to go to two places. And that is our new concentration, and concentration has the units of moles per decimeters cubed. Make sure to fill out the Google form and try those problems from the book.